This is an informal overview of the recent quantum ring-reduce paper that was completed during the Center of Quantum Technologies Hack Month in Singapore in 2026, and it's a collaboration between me and Randa Pera that kind of interconnects quantum communication and learning. So let's get started. This paper, this work, was based on the ring-reduce primitive, which is basically this foundational communication primitive for large-scale distributed training for things like machine learning models. It is used in models like Harvard, PyTorch GDP, and the NVIDIA Collective Communications Library. The way it works is you have a set of devices that are trying to train a model together. They are all training the same model, and the goal or the objective that they have together is to synchronize the model weights across different QPUs. So these gradients that you see in the different nodes of what represents the model. The reason why they have to do this, or the reason why this communication primitive exists, is because the model would be too large to share in one coordinated run. So we need to play around bandwidth constraints, so the amount of communication that two devices can have, in order for all the devices to have basically an average of what all the models trained were by every single device that was participating in the ring. The objective end state is that all devices share one consistent model. So in order for this to happen, there's two phases. There's a first training time phase where each device is basically training its model. And then there has to be a coordination time where each device is basically coordinating with all the other ones to reach that end desired state. Within the coordination time, basically what's going to happen between two devices is they're each going to have their version of the model that they've achieved after the training time. And they're going to want to share gradients of that model with the other device. So for instance, Alice is going to want to share this gradient 0 with Bob. Then what's going to happen is Bob is going to receive Alice's gradient 0 and it's going to add up its gradient. This is going to continue all through the round until F receives all the gradients and is able to average out to a final gradient 0 for this specific gradient in the model. This thing happens with all the gradients and all the devices in parallel until all the devices share one consistent model. So they'll each basically be responsible of one or multiple gradients depending on what's been sent to each other. And at the end, they'll do one final round and they'll send each other all their final gradients, and everybody will end at the end of that round with the same shared model. They might all be responsible for one gradient or multiple gradients, that doesn't matter. And as I've said, they'll all share one final model at the end. The complexity of this primitive is 2 to the n-1 rounds, and being the number of players, the number of devices in the field. And it's basically cut down, as I've said, in these two rounds, in the communication round and the final all gather round, and they each have n-1 complexity. Now, what would a quantum version look like of this primitive? This is the first question that we asked ourselves during the project. And what we thought firstly of was superdense encoding. So superdense encoding is this existing quantum primitive that basically enables Alice and Bob, so two players, to share 2 bits worth of information. The way it works is that in the classical world, if Alice wanted to send Bob 2 bits worth of information, well, Alice would do that. She would send 2 bits to Bob. But in the quantum world, we can actually play around with something. So we can set up a pre-processing step in which Alice and Bob are sharing an EPR pair, meaning they have 2 qubits that are entangled with each other. Then Alice applies some sort of rotation to her pair and then forwards her qubit to Bob. Once Bob has received this qubit, he can measure and now holds 2 qubits, so 2 bits worth of information, but actually the only thing that was shared was 1 qubit. So in some sense, this enables us to, in a setting where both bits and qubits cost the same, to say that superdense encoding is cheaper because you are using less units of information to send the same amount of information. Now, we thought that we could set this up in a quantum ring-reduce setting and basically set up some sort of relay race between all the devices, reducing the amount of communication necessary between each device by 2. This works, but it's not ideal. And a more ideal version of this same setup would be to have a GHZ state being pre-shared between all the devices. And instead of playing a relay race, we can have one shared canvas over which all the devices need to do this coordination. Setting up a GZ state in the pre-shared setting still kind of leads us to the same complexity as a superdense encoding, but it has a few nice add-ons properties that come with it. So the first one is that GZ states are the best quantum state for estimating any linear sum because they maximize Fisher information. They are, in a sense, probably optimal. But not only that, they actually come with privacy guarantees. You have to set up the shared state before any gradient is encoded, and you can verify it independently of the data that is forwarded. So you can, if you did some sort of encoding, you would only ever expose the global sum, never any individual gradient. So in a sense, it kind of assures some level of security that the classical communication could not assure by just playing this game of forwarding. So this is very nice and very interesting because obviously we've just talked about a very small but important in the sense of the billions of dollars and energy and water that would lead to advantage in ML training, large-scale ML training, but it's not very interesting for quantum people because these are very basic concepts in quantum communication. So we set out to ask ourselves, okay, we've now kind of looked at these basic advantages that mean a lot in the real world, but might not be very interesting for quantum people. What could be interesting in this setting for quantum people? So what we ended up as an answer to this question was aggregation problems. So we might have a setting where we have a training that occurs, and then that training needs to be communicated to a client, but that communication still is constrained with bandwidth. So the same problem that us and Bob had between each other, we are going to have with an external user that wants to learn after what the model is, even after it's been fully trained. In order to send that information, one of the things that can be done is compressing the model down to some sort of sketch. But compressing it down can lead to losses of information. You can, for instance, add on to gradients that are going to average out to zero, losing the information between the two gradients. And it's kind of, we can ask a lot of questions about, how could we make sure these things not happen, both in the area of the server sending the model down, but also in the setting where we're the user and we want to check that the data that we've been sending is consistent with our expectations of what the model should be able to do. So these aggregation problems, we translated them to a couple of games where we found advantage. The first one is margin conflict tension. So this comes from this idea of, can I set accurate and correct information from the point of view of the server? And basically, you can translate that question into, are gradients pulling together or canceling in some sense? If we're Alice and Bob and we both have different gradients, the same model, but different results because maybe we trained on different data, can we check if our gradients are in some sense aligned? The way that the question was formulated in the paper is as follows. And we're basically, again, just asking if the gradient x of A and the gradient x of B can be safely merged, or if averaging them out will cancel the signal. So, in the classical sense, setting, in order for them to be able to make a decision, basically one of them needs to forward its gradient to the other one, and they have to make a decision. So for instance, Alice needs to forward her gradient to Bob, so Bob can make a decision about gradient A and gradient B. But these bandwidth constraints, again, still exist. They still can't necessarily communicate all the information. So in order to send the gradient, they're going to have to send a compressed sketch. Sketching, basically, this compression just means sampling from the original data up to a certain error. It's a lower bound in the sense that you could potentially send the whole gradient if it fit, but if it doesn't, then you need to bring it down until you have too little information to be at the level of accuracy that you want. So this is what the classical world needs to do. But the question we had is like, what can we do in the quantum setting? So this question of can two gradients be safely merged or will averaging them out cancel can be translated to basically looking at wherever two vectors are pointing in the same direction or not. How far away are they from each other in terms of an angle? In our quantum setting, we take two normalized gradients because that's the input of our problem. And we basically look at wherever the inner product of these two normalized vectors would conflict or not based on exactly that, on wherever the angle is superior to, I don't know, 90 degrees, whatever our accuracy or our objective is. This we can do thanks to basically a combination of gap inner products and amplitude estimations by playing around with projections. Essentially, we are, instead of having one-way communication where Alice tells Bob her entire gradient sketch, what we have is Alice and Bob basically passing to each other reflections that accumulate into the rotation of the things that they're passing, of the information that they're passing, until they've made enough round trips that their accumulation of their reflections leads to the desired outcome, wherever that is accepting because we've reached the desired precision or not. So we suddenly reduce the classical communication to 1 divided by the precision instead of the precision times power 2 times log p. So we've reduced the amount of communication of total information that we need to transmit to each other, and this could intuitively come with a cost of time, but not necessarily, in the sense that there's no reason to believe that us playing around with these round trips, especially at scale, where this advantage of the amount of information that we're sending could be very visible, would take more time than just sending a lot of different batches of this compressed sketch one way. Now, that's not really, quadratic advantage is not really exponential advantage, right? So what can we do? What type of game can we play in a setting that is relevant to problems related to ring or reduce that would give us quantum exponential advantage? The problem that we came up with was relational sign audit. So this original problem of I've got a server, I've got a client, and the client basically wants to know that given their knowledge of the model, is the relationship that they're looking at true or not? They know that the server is going to send them a compressed update, and they want to know if that update is respecting the parts of the model that they know are tied together, that they have some relationship that they are expecting. The way in which we formulated this problem is a bit long, but essentially we're asking if, given what we know, so that some gradient pairs should be pushed in the same direction, they should both be plus, they should both be minus. We want to check if there's consistency with that knowledge given the received information. It's basically an instance of Boolean hidden matching, and you can think of it as some sort of a Where's Waldo game. In the classical setting, in order to complete that, we've got to have a square root p of bits, p being, p to the square being only possible pairs that we have of our gradients or our information. Because there is a Boolean hidden matching lower bound that tells us this has to be the case. The classical server, in a sense, must be able to answer every possible pairing in advance for all the possible pairs. But in the quantum setting, we can do the following. We can encode each parameter, write each parameter into an amplitude of its own basis state and basically send forward from the server to the user a phase state that would be encoded into log p qubits. From there, with this state, we can just start doing a series of pair basis or parity measurements, and basically, by definition of what those measurements mean, randomly land on pairs and return wherever they agree or disagree. We keep doing that, the amount of rounds necessary to reach the accuracy that we desire, and we basically end up in a setting where the quantum server can send one state holding all the signs, and the client's measurement can basically randomly pick pairs it cares about and check wherever they are consistent with what they're expecting. This means that we have an exponential advantage in this problem whilst not changing the framework of working or sending information one way. Now, what are the conclusions of our work? Well, we got some modest reductions and some nice pre-security on one of the main communication primitives used today in large-scale ML training, which is very useful but a bit boring for quantum people. And we also found a set of related problems which offer quantum advantage and point to complexity landscapes, where certification and evaluation of relational properties could point to quantum advantages, which is very interesting, but perhaps not useful or not as useful today. And yeah, feel free to check out the paper and perhaps see you at QTML, sorry.